In previous lessons, the features of ramp were explored, in particular those related to simulating the energy demand of railway stations. In this lesson, ramp will be applied to calculate the traction energy demand, which is the energy required to move a train along its path. First, the key equations that describe train traction will be introduced, followed by their implementation in ramp. Next, a case study involving a real Italian route will be presented. Finally, different applications of this model will be discussed. Now, let's take a look at the fundamental equations that describe train traction. Since ramp calculates energy demand as the power of an appliance multiplied by the usage time, we can apply this approach to train traction. The traction power is calculated by multiplying the traction force by the speed of the vehicle. The traction force required to move a train consists of 4 key components. First, the Davies equation, which is the quadratic function of the train's velocity. It accounts for the vehicle's mechanical and aerodynamic resistance through the A, B, and C parameters. The presence of tunnels, represented by the tunnel factor, is also taken into account, as it increases air resistance. Next, the slope component considers the inclination of the railway track and the gravitational force acting on the train. Then, the acceleration components accounts for the train stops along the route, as the vehicle requires additional force to accelerate after each stop. Finally, the curvature component addresses the additional mechanical resistance due to the curvature of the track, and it is a function of train's maximum velocity. The features of this energy demand model tailored for railway sector can be described as follows. First, the model is bottom-up because it relies on fundamental technical inputs such as mass, acceleration, and mechanical parameters. Next, it is a stochastic model, as ramp allows for the randomization of power, usage time, and train parameters. Finally, the model is open source, ensuring transparency by using train and route data derived from literature or open access databases. Now, a case study will be presented. We will consider a real route in the southern part of Italy, for which measured data is available. The train under consideration is an Italian ALN 668-3000, weighing 37 tons. The maximum speed of the train is 130 km per hour, while the average speed is 103 km per hour. It is a conventional train, so corresponding values are assigned to the mechanical and aerodynamic parameters. In addition, the energy consumption of auxiliary systems, such as HVAC and lighting, is considered, typically representing around 20% of the total traction energy. The track is approximately 177 kilometers long, with around 5 kilometers of tunnels. The train makes 13 stops along the route. The average inclination of the route is about 5 meters per kilometer. Upon checking the results, the error between the calculated value and the reference one was around 6%. Therefore, the model can be considered validated. After successfully applying the model to the specific route, the model could be extended to every route in Italy, enabling the simulation of energy demand on a national scale. Additionally, the traction demand model can be integrated with the station demand model, allowing for a comprehensive analysis of the entire railway sector. This approach can also be used to localize energy demand hotspots within the national railway network, facilitating better integration with renewable energy sources. The model can also be used for scenario analysis, such as examining the potential evolution of Italy's high-speed rail network. Finally, the model can be applied to other countries, thanks to its open-source design. In conclusion, integrating the traction energy model within RAMP provides a powerful tool for simulating and analyzing energy consumption in the railway sector. By applying a bottom-up stochastic approach and leveraging open-source data, the model is both versatile and scalable. The case study of the Italian route demonstrates the accuracy and practical application of the model. This paves the way for the model's extension to national railway networks, enabling comprehensive energy analysis at a larger scale. Moreover, its open-source nature enables adaptation to other countries, providing valuable insights for optimizing energy use in railway systems globally.